Okay, so as I was preparing for this video, I discovered that in the software I can generate a lightsaber, and I can even make two of them and have them maybe like fight against each other. So I don't know, I'll try to think of ways to use this in a video. If you have ideas for me, please let me know. But anyway, so today we're talking about energy. Well, we're actually talking about work, okay? But first let's talk about energy, okay? And so as a teacher of physics, I can't think of a concept that's more difficult to communicate than energy. And there's different definitions of energy in physics, in chemistry, in biology, and yet it's very important. It's a very important theme that connects all of these content areas. And energy is such an important concept, but it's really hard to talk about. So how do you even define it? And so one of the ways I want to think about it is, let's say you have an object, okay? Well, this object can only have energy if there's other objects around it that it can relate to, okay? So like you've talked about kinetic energy before probably. Well, kinetic energy is energy that has to do with how fast something's moving. Well, velocity is relative to another object. So kinetic energy would be relative to another object. And so the first most important thing when we talk about energy is to talk about a system, and energy within a system. Okay? And so this object right here can have energy because it's part of this system, and it would have energy as it relates to other objects. Let's add some other objects to this system. So now we have a system with multiple objects. So now we have this system, kind of looks like a pumpkin, and we have these three objects in it. And now these objects can have energy because there's other objects around them. And so energy is kind of what is going to allow us to describe the relationships of these objects, okay? And so this is, again, a really abstract definition. But it's just really hard to come up with a definition for energy because it ends up being very circular, okay? And so I'm going to take a step back from this. We'll come back to this in a second, okay? And so now we're going to talk about, we're going to do a little bit of a derivation. So if we look at the equation for Newton's second law, that the net force is equal to mass times acceleration, okay? And we're going to do some science here. We're going to do some physics, so we're going to do a derivation. We're going to combine it with this equation right here. V squared equals V naught squared plus 2 times A times delta x. Okay, and what I'm going to do is I'm going to solve this equation for A. So acceleration is equal to net force divided by mass. And if I put this into this equation here for acceleration, I get that V squared equals V naught squared plus 2 times F over M times X. Okay, I'm going to do some quick solving. I'm going to move the V squared over. So V squared minus V naught squared equals 2Fx over M. And so I'm actually going to solve this for F times X. So I'm going to divide over 2. I'm going to multiply over M. And so I get that V squared minus V naught squared times M over 2 equals F times X. Now, this piece right here we can simplify by distributing the M over 2. And so we could say, okay, if we multiply M over 2, we can say, all right, 1/2 times M times V squared minus 1/2 times M times V naught squared is equal to F times X. Okay, so now we've come up with this. So I don't know if you recognize this term here and here, but essentially, I mean, that's the equation for kinetic energy. So this derivation right here is where the equation for kinetic energy first came from. Okay, so we define kinetic energy, or the energy that a particle has because of its velocity, as 1/2 mv squared because of this equation. Now, before this, it was just mv squared, and then because of this derivation, they actually changed the equation to be 1/2 mv squared. Okay, and so if we replace 1/2 mv squared with kinetic energy, then we can rewrite this now. I'm going to see the next slide. We can rewrite this now as the change, right? 1/2 mv squared minus 1/2 mv initial squared. So the change in kinetic energy is equal to a force times a displacement. And really the net force times displacement. Okay? So if you think about this, if you push something and it moves in the direction you're pushing it, then if you're the only force acting on it, then you're going to increase its energy. So you're going to make it go faster. And so you're giving it energy. Okay, and so that's basically what this relationship is. In this part over here, we define the force times the displacement. We call this work. Okay, so whenever you exert a force over a distance, you're doing work. And you're causing the kinetic energy of a system to change. Okay, and this is called the Work-Energy Theorem. Okay, and so now let's get back into our definition of energy. Because essentially, in physics, we say energy is the ability to do work. Okay, which means that energy is the ability to increase the kinetic energy of an object. Okay, or you could say that work is the change in kinetic energy. So we're defining energy and work with energy. So it's a circular definition, and that's why it's so hard to understand or so hard to describe. Energy is a property of matter. Okay, and it's a way that we can talk about the interactions of matter, and it's a really, really useful tool in talking about that. Okay. So anyway, that's the basics there with kinetic energy. So we'll just do some quick calculations to finish this off. So we can say, okay, well, let's say that you have an object with a mass of 3 kilograms, and let's say that it's traveling 5 meters per second. What would be its kinetic energy? Go ahead and solve. Well, kinetic energy, 1/2 mv squared. So when we plug those in, 1/2 times 3 times 5 squared is 25. So that'd be 75 over 2, or 37.5 joules. Okay, so the next thing to know is that energy, the units of joules, 1 joule is 1 kilogram meter per second squared, right? The unit for force, times a meter, and so a joule is 1 kilogram meter squared per second squared. Okay, and so that's why we're able to have 37.5 joules there. And what the thing that's really bizarre here, and that's not the right term. The thing that you need to pay attention to is that joules are a scalar. Energy is a scalar. Okay, and in this equation you had velocity, and velocity is a vector. And you do this calculation with a vector. You do this calculation here with a vector, and you end up here with a scalar. Okay, the exact moment that the vector turns into a scalar, I believe, occurs right here when you square it. Okay, and we're going to dig a little bit deeper into this in the next video. Okay, when we talk a little bit more about vectors and energy. Okay, but this is the basics, how to calculate kinetic energy. And so now let's think about how we could use the Work-Energy Theorem. Okay, that work is equal to the change in kinetic energy. Okay, well, what we can say is, well, let's say that there's an object. And let's say that this object has a mass of 2 kilograms. And let's say that this object has a velocity of 5 meters per second. And let's say that this object is sliding along a rough surface, okay? And it's going to slide to a stop, okay? Well, what that means is that its kinetic energy is going to change to 0. If it's stopping, the kinetic energy will change to 0. And so we can use this work energy principle that work is equal to the change in kinetic energy if we want to find out let's say, how far away or how long it took to stop. If we want to find out how far it's sliding, we could use that. And so let's say that it experiences a coefficient of friction of 0.4. Okay, so what we can do here is we could say, okay, well, the kinetic energy is going to change. So I have change in kinetic energy, which would be final minus initial. So at the end, we have, so mass is 2 kilograms, and at the end the velocity is equal to 0. Okay, and then at the beginning, my initial kinetic energy is 1/2 times 2 kilograms times 5 meters per second squared, or meters per second, okay? And so that's equal to the work is equal to that change. Now, on the side with work, well, that's the force that it experiences times the displacement, okay? And what you're going to notice is that when I do this calculation, I get 0 minus 2 times negative 1/2 is negative 1 times 5 squared is 25, so minus 25. So I get a negative change in kinetic energy. Okay, and what that means is that negative work is done. And so the reason that we say that negative work is done is because energy left the system. And there's kind of a rule for when negative work is done. Whenever the force that's causing the work to happen is acting in the opposite direction of the displacement, in those cases work is negative because work is done to take energy away. So think about a scenario. What's an example of when you use a force to take something away? You could think about like if you're catching a ball. You're exerting a force one way, the object's moving the other way, you're taking energy away from it. Okay, whenever you're slowing something down. So whenever a force slows something down, it's doing negative work. Okay, and so force times displacement on this other side, so we wanted to calculate how far this box is going to slide. So we're going to use, say, the force is friction, that's the only force acting on it, and we'll say it's a negative force, because we'll say that this way is positive. And so free body diagram, we have weight, we have normal force, and we have this frictional force acting backwards. So let's say negative mu times mg times x, okay? And so m is 2, we'll use 10 for g, okay, and then mu is equal to 0.4, okay? And so we can say, all right, well, 8 times x is equal to 25 joules, and this is negative, so then the displacement would be 25 over 8, or about 3.1 meters. And so what that tells us is that this object slid 3.1 meters as it was being slowed by friction. Okay? And so this is the basics of the work-energy theorem. We're going to get deeper into this over the next couple days. And really what this comes down to is it's an alternate method for solving problems and for approaching problems. Because anything that, let's not say anything, but almost everything that we can do with the work, or a lot of things that we can do with the work, are things that we could do using kinematics and Newton's laws. But sometimes it's just easier to use work, okay?